Welcome to Chemistry at Hananiga High School. I'm Brian Brown, and today we'll be looking at our second day's worth of notes of Chapter 2, where we're looking at the second section. And we're studying our subatomic particles and the nuclear atom. So we're looking at how do we know what we know about the atom, who discovered it, and how. So you have a better understanding of the parts. Now, we had Dalton's atomic theory, which had these small indivisible particles. And our first contributor to changing that fundamental picture was J.J. Thomson. In 1897, in the cathode ray experiments, Thomson discovered that all substances were made up of a same fundamental particle of negative charge, and he termed it the electron. Now, how he did that in the cathode ray experiments, here is an example of a cathode ray tube. Now, you can see that we've got a tube that's hooked up to electricity. You put an element inside that tube, so some gaseous element, and you hook up the electricity and nothing happens. That's because there's something there moving through that tube that I can't see with many gases. So what they did was they put a phosphorescent sheet inside there. And Crookes was the person who came up with this. So that's really who discovered the cathode ray tubes. But Thomson used it to figure out that all these substances contained electrons. So there was a beam of something moving across that phosphorescent uh, piece of paper in there would then show was actually moving across this. So as these mysterious rays were hitting the phosphorescent sheet, it would make the phosphorescent sheet glow. And you can see that the one side of a magnet actually makes the beam bend towards the magnet. It's because magnetic fields also generate electrical fields. And so when you flip the magnet, it's actually going to repel rather than attract. So he knew whatever this beam was, it was negatively charged. Now, what's this charge to mass ratio that he established? Well, whatever was moving across there was actually depositing on the far side. Now, if he took out that plate on the far side, he could measure what its charge was, and he could also find its mass. So he could divide the two and get what he called the charge to mass ratio. Now, no matter how long he let the reaction go, the charge to mass ratio was always fundamentally the same. So these negative particles were being deposited on the end and were building charge and mass, and it was always the same charge to mass ratio. Well, what surprised him was when he put a different element in there, you had the same thing happen, and it had the exact same consequences. It had the same charge to mass ratio, and it was clearly negatively charged. And then he put another element in there, and he found out that all elements had this same fundamental particle that was inside them that was negatively charged, and he knew it was a fundamental particle because, and it was the same in all of them, because it behaved the same way and had the same exact charge to mass ratio regardless of the substance. So he came up with our first subatomic view of the atom. He said electrons, which are these negatively charged particles, were stuck to some positively charged mass, and that was basically what our atom was. So we still had basically this solid object, but it was a solid core with negative things stuck to it, and that's what our atom was. Now, I've got a brief review of what the cathode ray tube is, so you can check out this movie. It'll be linked online. But the next person to add to this was a scientist by the name of Millikan. In a very simple apparatus, an experiment, he was actually to find something that scientists didn't figure would be something that they could actually weigh, and that is how much does an electron weigh. We knew there were these small little negative particles, but how can you build a scale to weigh something that small? Well, the answer is you don't. What you use is indirect evidence to try and figure out what the mass is. So in the oil drop experiments, he actually determined what the mass of an electron was. And it was a really simple apparatus. So you took a oil and you put it in a atomizer over here on the far left. And that's basically like the old perfume sprayers. And what happens is when you squirt it, the liquid that's in there gets dispersed as uniformly sized little tiny droplets. Now those droplets are more dense than air, so they're going to fall. So in that top chamber, they basically fall down. Now there's a charged plate in there with a hole in it. And what happens is at that hole, there's an electrical field that the drop passes through when it's falling through the hole. And what's really happening is electrons are getting stacked on the oil drop. Now, it's not going to be a consistent number of electrons. So depending on a number of factors, the oil drop as it falls through is going to pick up electrons. Now, as that oil drop continues to fall, now it has a negative charge on the outside. So at the bottom, he has a negatively charged plate that he can change the voltage of. And when he increases the voltage, it's going to create a stronger negative repulsion. And eventually what's going to happen is those oil drops are going to start to slow down in their fall simply because they're being repelled by that bottom plate. And you could increase the voltage and you could get that oil drop to fall in place at a specific spot. And what he did was he wrote down what the voltage was. And then he froze another oil drop and wrote down what the voltage was. And he looked at the differences in voltages between all of those things. So they must have collected thousands and thousands of bits of data. So this would have been a long, arduous, tedious process. So they collected voltages, and from those voltages, they could compare what the charges were, and then they looked at the difference in charges between side-by-side particles. And what he fundamentally realized was that every one of those oil drops was going to have some number of electrons on them, but it wouldn't be the same. But if he looked at the differences between side-by-side oil drops and kept looking at those charge differences, he realized that depending on how many electrons were on the two different oil drops, there would be a difference in charge. And if he could analyze all that data and find out what all of the change in charges were divisible by, that fundamental thing that they were all divisible by had to be the charge of a single electron. So all of the changes in charges in this simplified model that you look here seem to come in multiples of 1.602 times 10 to the 19th. So while his numbers would have been more complex than that, they would have all been divisible by this one value because he knew there had to be some whole number multiple of electrons that were on them. And the actual charge of a single electron would then be a whole number divisible by all of those charge differences. And at that point, he said this must be the actual charge then of a single electron. Now, at that point, he put it together with the charge to mass ratio of Thomson. So a charge to mass ratio allows you to convert back and forth between charges and masses. And since he now knew the charge of a single electron, he could use it to calculate the mass of a single electron. And he found out that it weighed a very specific, very, 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 very small amount in grams. Now, since it's such a small, meaningless number in grams, we're going to end up using what's called atomic mass units. A proton weighs 1 atomic mass units. In general, electron weighs about 2,000 of the mass of a proton. So yes, there are actual gram mass amounts that these deal with, but you end up with more odd numbers. So what he was able to do was calculate the mass of a single electron. And even with very primitive equipment, his value is in 1% of the accepted value of today. So with really simple apparatus, just by thinking through what had to be happening, he was able to determine the mass of a single electron with a great deal of accuracy. For that, he won the Nobel Prize. Next person that came along that changed our understanding or contributed to our understanding of an atom in a meaningful way was a scientist by the name of Ernst Rutherford. Now, in 1911, in his gold foil experiments, he discovered the fundamental structure of an atom was different than we thought it was in its day. Now, by this time frame, we were getting away from that what's called the plum pudding model of Thomson, where you had this positive goo or matter that negative things were stuck in. And scientists had a suspicion that maybe a lot of an atom was empty space. So he tried to come up with a way to test that. And what he did was he took something very dense like gold, took a very thin sheet of it, hence the gold foil experiment, and he fired at that sheet a small positively charged particle. It's actually a stripped helium nucleus. And with phosphorescent sheets, same thing that we used in the Crookes tube or the cathode ray tube experiments, he could then see what was coming out the far side of that thin piece of gold foil. And what he discovered was electrons are outside of some positively charged nucleus. The nucleus was a very massive but very, very small chunk in the inside of our atom. And he knew it had to be positively charged, which meant the electrons then were somewhere outside of it, because if the electrons were stuck to it, overall it would be neutral. So electrons are outside of this positively charged nucleus. And that he proved what he suspected was most of an atom was really empty space. Because where most of our mass of the atom is located in this tiny little dense object known as the nucleus with positive charge. Now at this point we didn't know that that positive charge was caused by protons and there were also neutrons in there, but we had this tiny little nucleus in the middle of an atom around which electrons moved. And that's pretty close to our modern view of the atom. So Rutherford gave us what looks recognizably to us as an atom. Now, just like before, there is a movie here you can see that actually shows you what's going on in the gold foil experiments. So it animates this idea. So he had a thin piece of gold foil. He fired alpha particles at it. to these small little positively charged particles. And he suspected that even though this was a solid piece of gold foil, if an atom was mainly empty space, most of the particles, because they were relatively small, should go straight through. But this stripped helium nucleus was still a relatively large particle. If it was hitting things of size in there, it should be deflected. But he figured what it was hitting wasn't really all that much larger than it. So he thought most of it would go straight through, and that's exactly what happened. But he thought every once in a while things should be deflected and changed a little bit as it struck the particles that were inside the nucleus. And sure enough, that's exactly what happened. What totally surprised him and his fellow scientists was that some of the particles were knocked backwards. And to him, that was totally, totally incomprehensible. It's like a bus bumping into a person and the bus bouncing off. That really can't happen unless the person is incredibly, incredibly, incredibly massive. So most of our mass of an atom had to be located in this nucleus, and that's why some of the particles bounce straight back. So we went from the plum pudding model of Thomson to this more recognizable view of the atom. Now, in 1920, we found out what some of those things were. Now, they'd suspected, but once again, eventually, Rutherford was able to determine that inside the nucleus, that positively charged thing, there are actually positively charged particles. So in 1920, he coined the idea of the proton existing, equal in, or I should say, opposite in charge of the electron. So equal but opposite in charge, and that was the proton. Well, we were still missing the neutron, the neutrally charged particles inside an atom, and that wasn't until 12 years later when James Chadwick in 1932 discovered the existence of neutrally charged particles inside the nucleus as well. And now finally we would have accounted for the mass of what we would expect to see in general inside an atom. So when you put it all together, what do we know and where are they at and what are the masses and charges and so forth of these particles? Well, first we've got the electron that was discovered first. It's E minus as its symbol. Remember, that's outside the nucleus, has a relative charge of 1 negative. Its mass is about 1/2000th of an atomic mass unit, which would be what um, the nucleus of a hydrogen atom would weigh, our most common form of hydrogen, hydrogen 1. And the actual mass in grams, like I said, incredibly small, 9.11 times 10 to the negative 28th. Now our proton is P+. It's in the nucleus. It has a relative charge equal but opposite to that of the electron, and it weighs 1 atomic mass unit. So atomic mass units are really based upon the size of the subatomic proton and neutron, and that's what the mass of the actual proton was. Now finally our neutron, our last discovered particle, and it was discovered last because it doesn't have a charge, so it's much harder to detect, is N0. It's in the nucleus. 0 is its relative charge, but it weighs essentially the same thing as a proton in both atomic mass units and mass. And that's an overview of our subatomic particles and how we know those things exist.